This is any equation in which we find a variable inside the power. Now, this could mean something as simple as 2 to the power of x is equal to 64, or something way more complicated like the following equation. If x happens to be inside a power of one of our bases, we call it an exponential equation. The goal of this lesson is to devise some strategies to solve these kinds of equations when our base is numerical. Let's discuss the procedure that we can use to solve exponential equations. The first thing we want to do is try to isolate the exponential expression on one side of our equal sign. Now, the reason we're going to do this is because of step 2, where we apply the logarithm with the same base to both sides of the equation. The reason we're applying the logarithm to both sides of the equation is because we know if we apply the logarithm of the same base that our exponential expression is in, those actions are going to undo each other because they're inverse processes, and we're going to be left with just the power. Sometimes it may not be possible to use a logarithm with the same base as our exponential expression, or in some cases we have two exponential expressions and we have to choose one or the other base for our logarithm. In this case, don't forget that you have the special power property of logarithms that you can use. So you're able to take that exponent and bring it down out front and treat it as a multiplication. So sometimes you may have to use step 3 to bring down the power to remove it from that exponential expression. And of course, our fourth and final step here is to solve for x, or whatever variable we have in our exponential equation. Let's begin by solving the following two examples. First, we're going to focus on 10 to the x equals 100. Now hopefully you can see that if I were to write this a little bit differently, writing 100 as 10 squared, you can see that the value of x here is probably going to be 2, or at least hopefully this convinces you that the value of x is 2. But let's work through the procedure so you can see exactly what's happening for cases where it's not easy to rewrite this right-hand side as a power of the base that's on the left-hand side. The idea is, because 10 is our base, we're going to take the logarithm base 10 of both sides. Since the base of our logarithm and the base of our exponential expression on the left-hand side are the same, their actions are going to undo each other and we're going to be left with the value of x. The same thing happens over on the right-hand side. The base of our logarithm as well as the base of our exponential expression are the same, so we're left with just the numerical value of 2. So this is the strategy that we use when the exponential equation doesn't simplify quite as nicely as the one we just did. For example, if we have e to the 2x equals 17, well, it's really difficult for us to think about 17 as having base e raised to some power. So what we do is we are going to take this exponential equation and we're going to use log base e to remove the base of e in our exponential expression. So we'll take ln of both sides. Notice here that since this is log base e, and the base of our exponential expression is also e, those actions are going to undo each other and we're going to be left with 2x over on the left-hand side. Over on the right-hand side, we're just going to leave this as ln of 17. That's the best we can do. There's no way that we can rewrite 17 using a base of e. Now finally, to solve for x, we could divide both sides by 2, so we get the following expression, ln of 17 over 2. Next, let's take a look at an example where the bases of our exponential functions may not necessarily be the same. I'm going to use the procedure and I'm going to apply a logarithm of both sides. In this case, you want to choose one of the bases to be the base of your logarithm as well. So I'm going to take log base 2 of both sides just to make the computations on one side a bit easier to handle. Since the base of my logarithm and the base of my exponential expression on the left-hand side are the same, I'm going to be left with 3n minus 5. The same thing does not happen on the right-hand side because the base of my log is 2 and the base of my exponential expression is 4. Now, that said, I can still use the power property of the logarithm here. I can take the n plus 1, which is the power, and bring it down out front and treat it like a multiplication. So on the right-hand side, we're going to get something that looks like this. It doesn't always happen so nicely that this logarithmic expression is going to simplify, but in our case, we can write 4 as 2 squared. And now we can see on the right-hand side that this is going to change into n plus 1 times 2. So I'm going to go ahead over on the right-hand side and expand that through to get 2n plus 2. And now we have a linear equation in n that we can solve very easily. If we subtract 2n from both sides, we're going to get n minus 5 is equal to 2. And we could add 5 to both sides to get n is equal to 7. In our last example, we want to solve the following equation. Negative 3 times e to the x plus 2 plus 12 equals 42. Our first step is to try to get this exponential expression all by itself. So right now we have this minus 3 and this plus 12 that are in the way, and I need to remove those before I can apply the natural logarithm to get rid of the base of e. So let's begin by subtracting 12 from both sides. This is going to leave us with negative 3 e to the x plus 2 is equal to 30. Next, let's remove this negative 3. So I'm going to divide both sides by negative 3. This is going to give us e to the x plus 2 is equal to negative 10. Now that we have the exponential expression all by itself on the left-hand side, now's a good time to apply the natural logarithm to both sides to get rid of this base of e. So the left-hand side does become x plus 2. But did you notice something here that went wrong? Maybe you recall when we started working with the natural logarithm that we can't have negative values inside of our natural logarithm. This implies that there are going to be no values of x that solve our original equation. Alright, my little epsilons, stay positive.